Hello, everybody. Thank you for attending my talk. And today I will talk to you about how to build specialized database for logs and why it is important, why it is not a good idea to use traditional databases, relational databases for logs, such as Postgres or MySQL. Let's meet. I'm Aliaksandr Valyalkin. I'm a software engineer, and I mostly write code in Go during the last more than 10 years. That's my primary programming language. I like Go because it is a very simple language and very productive language. It is easy to write fast code in Go, and this code is usually much easier to read and maintain compared to other programming languages which I was working before. And I like writing useful open source software, and I like making this software to work out of the box without needing of reading a lot of docs, without needing to perform non-trivial configuration. So that's the property which is missing in many open source projects, and I think that it's very important to end users. And I like creating servers optimized for speed and low resource usage. That's why I created VictoriaMetrics. It's an open source database for metrics. It is also named time series database. It is very efficient and fast. And recently I created VictoriaLogs. It's another database specialized for storing logs. What is logging? I think that everybody knows what is it, but let's repeat it again. The logging is a process of producing logs, and logs can have different types and sources. The typical sources is server logs, when you run some long-running service and this service generates some logs. There are also client application logs, when you provide some client applications, and when client runs these applications, they also may generate logs or different events, and it is a great idea to collect these logs and events in a centralized place in order to be able to investigate them, to collect some statistics and make some decisions on top of these statistics. And there are also web event logs or web analytics, such as Google Analytics, for example, or other analytics services. They generate log-like events with many different log fields per each interaction of visitor or user with your website, such as click on some link, navigating on this website, scrolling, and so on. And there is also such type of logs as industrial logs. These logs which are generated by some industrial equipment, for example, cars, industrial machines, some big factories. And it is also a great idea to collect them in central place and in order to analyze later. So the next step after we generate logs, we need to collect them and store them in some centralized database for simplifying future analysis of these logs, and collecting and querying the collected logs. And also the important step for logging is archiving old logs into some less expensive storage, such as object storage, for example, and deleting old logs when they are no longer needed. There are a few types of logs. The first type is regular plain text logs. I think that the majority of this audience already familiar with these logs. That's just plain text logs. This is an example which can be generated by any applications. These logs usually have custom structure or have no any structure. In this case, they have some semi-structure with timestamp which goes first, then log level, and then allocation of this log source, and then some plain text string with some information. And another type of logs is structured logs. The difference between plain text logs and structured logs is that structured logs contain some fields with predefined names and values. For example, this one here, an typical example of structured log, which contains some fields for some application which runs obviously in Kubernetes in some container. So it contains log fields for this container, and it also contains log message, which is arbitrary text string, and some other fields. And there are also void events. Void events is the same as structured logs, but the difference is that void events can contain hundreds of individual fields per each log. You can read more about log events by this link. I recommend you reading this blog post. It's very well written and eye-opening if you don't know what void events mean. And as I said, void events usually contain a lot of many log fields, hundreds of log fields. And here is a post from Charity Myers. She is famous in observability space, and she recommends collecting as many as possible different log fields in void events in order to simplify further analytics over these logs, further investigation of collected logs or void events. When logging becomes large scale, my talk is about large scale logging. So let's decide probably when we reach gigabytes of logs per day. Who thinks so? Nobody? Okay, probably a terabyte of logs per day. Yeah, it sounds more like large scale. Okay, how about petabyte of logs per day? Okay, and I think that logging becomes large scale when these logs cannot fit a single computer. That's my definition of large scale logging. When you cannot fit logs into one computer, then this is large scale logging. Otherwise, it's small scale logging. And this all depends on the size of the computer you use and the database you use. Because if you run this on some Raspberry Pi and store logs in Postgres, then probably a gigabyte of logs per day is really large scale. But otherwise, you can run some specialized database for logs on some very beefy computer with hundreds of CPU cores and terabytes of memory. And in this case, this computer can process and store really petabytes of logs in a single computer. And in this case, even a petabyte of logs doesn't sound like a large scale. Okay. how to store a petabyte of logs on a single computer. Let's look at computer in in Google Cloud. When you look at the Google Cloud, then a single computer is allowed to attach to it up to 64 terabytes of storage. I would say that a typical maximum size of storage which you can attach to an average computer. Of course, you can attach more this storage to some specialized computers which cost millions of dollars, but typical case is this one. So we are limited to 64 terabytes of disk storage per computer. How to 1 petabytes of logs needs 16 64 terabytes disks, and how to cram this petabyte of logs into 64 terabytes of disk space. Any ideas? No? Okay. The answer is simple. It's just compress these logs by more than 16 times, and that's it. And this is very real, because typical compression ratio for logs stored in specialized database for logs is in the range between 8 and 50 times. And it's according to my experience, to experience of users of VictoriaLogs. So we can compress an average typical logs, petabyte of logs, into 64 terabytes and store them on a single computer in Google Cloud. And we can store even more logs if they compress better than 16 times on a single computer. With the only exception is that this is possible only when you use specialized database for logs, and it is impossible when you use Postgres or MySQL. And how specialized database for logs can achieve such high compression ratio for typical logs? Because if you try compressing typical logs without any transformations, you probably achieve 10x compression rate in the best case, especially if these are logs which contain which are structured and contain many different fields, and structured logs are represented as JSON lines. And that's magic for specialized database, but in reality, reality is simple. Such specialized database usually splits structured logs into individual columns per each log field, and store every value for every individual column in blocks, and process this data in blocks and compresses this data in blocks. And if usually many fields in structured logs contain similar values, and these values compress very well up to 1,000 times. If, for example, if you store some constant or some value which can have a small number of values, for example, such as log level, for example, info, error, warning. We have 3 different values, and these 3 different values can be compressed very, very well if we store them in a single together in a single column. And another feature which allows achieving high compression rate is to use specialized codecs depending on the shape of data per each column. Databases can automatically detect the type of data per each column and apply the best codecs which reduce the size of these logs on disk and which improve query performance. For example, they can detect constants, enums, numbers, timestamps, IP addresses, and so on. How to improve query performance of a petabyte of logs? Let's look at the example. The modern computers have disks with the maximum disk read I/O at around 4 gigabytes per second. These are NVMe disks. And when we calculate how much time it is needed to read 1 petabyte of data, by dividing 1 petabyte by 4 gigabytes per second, you get around 70 hours. And that's quite slow. Okay, we forgot that we already compressed this logs, 1 petabyte of logs to 74 terabytes. And 74 terabytes can be read in 4 hours and 27 minutes. It is better than 70 hours, but still too long to wait. Okay, what we can do next? How to reduce query time next? How about skipping reading unneeded log fields? If we store structured logs have many log fields, and if the query only needs a few of these log fields out of a big number of log fields, then why we need to read the rest of the log fields? Okay, suppose that we have log messages with log entries with a log message and big number of log fields, like in the example shown for structured logs I showed before. And suppose we only need to read 4 terabytes out of 64 terabytes of data for the given query. And in this case, the query duration will be reduced to 17 minutes. That's much better, but we can go further. If we automatically partition stored logs by time, okay, step back. What is partitioning in database? Partitioning in database means that some rows in this database are physically grouped and stored in some physical locations close to each other. Each partition, each data for each partition are stored physically close to each other. For example, you can store each partition in a separate directory in file system, or you can store each partition in some contiguous space in file. So, return back to the partition logs by time. We can partition logs by time, and when we execute some query, we can quickly skip partitions outside the requested time range without reading this data. For example, we have 30 days retention for logs, and our query needs reading only 3 days out of 30 days of retention. And in this case, we can reduce the amounts of data which should be read from disk from 4 terabytes to 400 gigabytes, and 400 gigabytes can be read from disk in 1 minute and 40 seconds. So the query time for 1 minute and 40 seconds looks good for terabytes for a petabyte of logs. But we can make it even faster by partitioning logs by another dimension. And this dimension is named log streams. What is log stream? Log stream is ordered logs by time which are received from some application instance. For example, you run many servers, and every server generates some logs and generates a single log stream, and we can store a single log stream into partition, virtual partition close to each other on disk, and index it additionally to other information in these logs, and we can use this index during querying in order to reduce the number of log streams which we need to read during querying. For example, we have 1,000 log streams in our database, and only 100 log streams need to be inspected during querying. And this allows us reducing the amounts of data which we need to read from disk from 400 gigabytes to 40 gigabytes, and the 40 gigabytes can be read in 10 seconds on this machine. So we reduced the query duration from 70 hours to 10 seconds for a database which runs on a single computer and stores petabyte of logs. Sounds impressive, but we can go further. There are typical types of queries for logs when you need to get some logs which contain some unique or rarely seen substring or phrase, such as trace ID, user ID, or IP address, or something like that. And we can use Bloom filters for reducing the amounts of data which needs to be read from disk in this case. What is Bloom filters? This is a probabilistic data structure which answers a simple question whether the given item exists in the given set of items. And why it is probabilistic? Because it may return incorrect answer. It can say, yes, this item exists in this set of items, but in reality, this item might be missed here. But we can reduce this probability to very low levels and use it, take advantage of this for log databases. And Bloom filters have a nice property that each size of Bloom filters is usually much smaller compared to the size, total size of original items for this Bloom filter. So what is an idea? An idea is simple. Let's split logs into word tokens and put all these word tokens into Bloom filters. And during querying, let's consult Bloom filters before reading the actual logs. Yes?
Roughly how much storage would this take for your petabyte of logs?
For Bloom filters, well, I will show you in the next slide. Okay, so if Bloom filters say that there are no such words in the data block, then we can skip reading this data block and save time for reading this. And in typical cases, the size of Bloom filters is from 10 to 100 times smaller compared to the original data in compressed form. And this answer for your question, if you have 64 terabytes of compressed logs, then Bloom filters may take around 6.4 terabytes, or starting from 600 gigabytes up to 6.4 terabytes. And this obviously improves query performance, may improve query performance by up to 100 times compared to the case when we need to read all these data blocks and inspect every log stored in these data blocks. So we can scan logs for some unique trace ID at a very impressive speed. Let's calculate it. It can be calculated as the discrete speed multiplied by compression rate. In our case, it's 16, and multiplied by this Bloom filters multiplier. And if we put numbers to this equation, we get that we can scan logs on a single computer at the speed of 6.4 terabytes per second. And that's not some theoretical numbers, that's real numbers from production. And let's return back why Postgres and MySQL aren't good for storing petabytes of logs on a single computer. During the previous day, there was a talk, probably in this room, about Postgres and how Postgres can store petabytes of data, actually. And this talk contained many interesting details and interesting problems which can occur when you try storing more than a terabyte of logs into Postgres. And there are many different problems, and I do not recommend you trying to store to MySQL and Postgres such big amounts of data, more than terabyte, actually not petabyte. So the first problem is that traditional databases store rows in row-oriented format. This means that they literally store every field for every row, one after each other, physically on disk. Why it is bad? Because this requires reading all the log fields when you need to perform some queries. Even if these fields are not needed in these queries, you still need to read this tuple of every field, of every row from disk, and then skip unneeded fields and only use the fields you need. And row-oriented storage also reduces compression ratio significantly, because individual rows, which contain many fields, compress at lower ratio compared to when you compress every log field values together. And not saying about that NISA, Postgres, MySQL do not compress data by default. They store data in uncompressed form by default. Also, Postgres and MySQL do not store related rows close to each other on disk. They do not partition automatically the stored rows. You need to say, of course, you can set up this partitioning on yourself manually, but they do not do this automatically. And this results in two problems. The first problem is that this increases the number of disk six needed to read individual rows. For example, you need to query some logs on the given time range for the given log streams, and in Postgres or MySQL case, this will end up in reading these millions of logs randomly across random locations in disk. And this will end up in a million of individual disk6 and disk read operations. And contrary to this, when you use specialized database for logs, it can store these logs compactly together to each other on disk in a single partition, and read all these millions of logs, information for these millions of logs, by a few disk I/O operations and at much faster speed. And this also increases the amounts of data which needs to read from disk, because disk internally on the operating system level and lower levels cannot read data in 1 byte granularity. They read data usually at 4 kilobyte blocks. This means that if you need to read only 1 byte from disk, in reality the disk will read 4 kilobytes of data and return only 1 byte out of these 4 kilobytes. And if you need to read rows from million different locations by and each row contains, for example, 100 bytes. In reality, you will need to read not 100 megabytes of data, but 4 kilobytes multiplied by 1 million, 4 gigabytes of data. And this becomes extremely slow and efficient when millions of, what I was saying before, when millions of individual rows must be read from different locations on disk. And MySQL and Postgres use B3 indexes for fast access to the given row on disk. B3 indexes serve well for traditional databases, but they do not serve well for logs. Why? Because the size of these indexes is usually quite big compared to the size of data stored in the database. It's comparable to the size of data. I put here 30%, but that's just number out of blue. But it's comparable. The point is that the size of indexes in databases is comparable to the size of data. And in order to be fast, all these indexes must fit into memory on a single computer. Otherwise, everything will be very, very slow. Data ingestion and querying, because during data ingestion, these indexes must be updated for each ingested row, and during querying, these indexes must be inspected at random order, I would say. This means that they need to fit in memory, otherwise you need to constantly read these indexes from disk. And computers with terabytes of RAM are expensive and rare. Yeah. And we have no computers with a petabyte of memory. And index is also slow when when you need to read not only a single log row from disk, but millions of log rows from disk. This is a typical case for databases for logs when you analyze logs. And in this case, indexes are also very, very slow. B3 indexes, I mean. And another issue with traditional databases is that they usually overwrite the existing data on disk in small chunks. For example, let's return back to this B3 indexes. The B3 data structure is built in the way that it needs to update its nodes or leaf nodes or intermediate nodes during adding new items to these nodes, and this usually is implemented as updating this data directly on disk. But when you return back to SSD on NVMe disks, probably you already know that they cannot write data on a single byte granularity. When you write or update some single byte in these disks, in reality, these disks read a block of data of half megabyte, then update the needed byte, and then write this block of data to another location. And this means that this load on disks, which is generated by traditional databases, is very, very bad for SSDs and NVMe disks. And it's very, very slow. Okay, what to do when a single computer cannot handle more logs when we enter this large-scale logging space? The first step which I recommend you doing is to switch from Postgres to normal database optimized for logs. It will save you nerve cells, and it will save you your costs, because you can continue using the same computer but storing to the same computer 10 times more logs or 100 times more logs, and receive the same or better query performance. So this first step is to switch to normal database for logs instead of using Postgres. And if this doesn't help, the next step is to scale horizontally to multiple computers. These steps should be done in this particular order. I don't recommend you starting with scaling horizontally for Postgres or for other databases, because before reaching this scalability limit for vertical scaling on a single computer, because this increases operational overhead, this increases everything, this increases costs, and so on. So choose the first pill, specialized database for logs, and then if this doesn't help, then choose the next pill, horizontal scaling. And which open source databases for logs to use? There are multiple choices. The first is Elasticsearch. The second choice is Loki from Grafana. The third choice is ClickHouse. It's very fast analytical database, and it has been appeared that it fits well for use case for storing and querying logs. And the last option is VictoriaLogs, which I created, and I recommend you using, of course, guess what? VictoriaLogs, because Elasticsearch doesn't scale well. It needs a ton of memory. When you want to store petabyte of logs into Elasticsearch, be ready to spend tens of millions of dollars on the infrastructure for this case. Loki is quite good, but it has some problems with too complex configuration and operation and upgrading. And it also has issues with high cardinality log fields, which contain big number of unique values such as trace ID, user ID, or IP address. ClickHouse is good, but it is good only if you know how to properly configure it, how to properly create table databases, how to properly choose partitioning, ordering for this log fields, and so on. So I still recommend you trying VictoriaLogs. And a bit of advertising for VictoriaLogs. It is open source database optimized for logs, and it includes all the optimization techniques which I mentioned on the previous slides. And these optimization techniques are enabled by default. You don't need to enable them, and they work automatically, automagically. And it can easily handle hundreds of terabytes of logs on a single computer. Probably it can handle a petabyte of logs on a single computer. But we have users who successfully ingest and query hundreds of terabytes of logs per single node of VictoriaLogs. And if you reach scalability limits of single node, then you can scale horizontally to hundreds of individual computers if you need to handle tens of petabytes of logs. And the horizontal scalability is very easy to achieve in VictoriaLogs, because you just add new servers, VictoriaLogs servers, and put in front of this VictoriaLogs servers two components. The first component is named VL insert. It accepts logs and then evenly spreads these logs across all the storage nodes. And the second component is VL select. It accepts queries and pushes down this execution of these queries across all the storage nodes. All the storage nodes pre-calculate everything they can, and then select node performs final calculations. And you can run, as I said, hundreds of individual storage nodes for VictoriaLogs, and it works very fast and efficient. VictoriaLogs also supports popular data ingestion protocols for logs, such as Elasticsearch, Loki, JSONline, Fluent bit, and so on. syslog, actually it also supports syslog, and it supports syslog very well. You don't need separate server, syslog server, for collecting logs into VictoriaLogs, because VictoriaLogs has built-in syslog server. You can just send logs over UDP and TCP to VictoriaLogs, and it automatically parses all the syslogs into separate predefined columns, fields, and stores the data. And VictoriaLogs is very easy to configure and operate. It is basically zero configuration. It runs good with default configuration options, and it is schemaless. You don't need to specify any schemas when you work with VictoriaLogs, when you send logs to it. And it can scale from very small computers, such as Raspberry Pi, to very big computers, such as some large mainframes with hundreds of CPU cores and terabytes of memory. And you don't need to optimize or tune its config options for both cases. You can run the same binary with the same options, without any options, configuration options in both cases, and get the maximum performance in both cases. So I recommend you trying VictoriaLogs right now after this talk, starting from home lab, and if you will see that it works great, then you can try adding it to your production environments with petabytes of logs. And let's look at some reviews from real users of VictoriaLogs. No, that's not our user, but just for fun. The first review is from some user who successfully replaced Elasticsearch cluster with 27 nodes and around 600 CPU cores and 4.6 terabytes of memory with a single node VictoriaLogs instance, which runs on 8 CPU cores and 64 gigabytes of memory. And he's very happy, and he ingests 1 million of logs per hour into VictoriaLogs, and he says that everything works good, and random search queries return a fraction of a second. And you can navigate this link and read the real publication from this user, and probably communicate with this user and reach him and ask what he thinks about VictoriaLogs. That's another review from about VictoriaLogs. This user who compares performance of grabbing of logs versus querying of logs stored in the same logs stored in VictoriaLogs. I highly recommend you reading this article. It's a very entertaining article, and obviously it shows that VictoriaLogs outperforms regular grabbing by multiple orders of magnitude in different types of queries, which are usually executed, performed during logs investigation. And let me say that I'm a very big fan of grep. Grep is my favorite command in Unix, and I'm a Unix user, Linux user for the last 20 years. And I use grep on a constant basis, tens or hundreds of times per day. So grep is great, and grep is great for logs, for investigating locally stored logs. But if you want achieving higher speed, and grep is very performant. It can scan literally gigabytes of logs per second on a regular laptop. But you can achieve higher speeds and higher performance for different analytical queries when you store these logs into VictoriaLogs and then query them. And another use case is True Foundry company migrated from Loki, Grafana Loki to VictoriaLogs and get very good results. The much smaller CPU usage, memory usage, 5 times less memory usage, or more than 5 times. 9 times less memory usage and 4 times less CPU usage for the same workload. And the performance of queries up to 20 times faster. 94% means that its numbers are slightly misleading. 94% faster means that in reality this query performance is up to 20 times faster, because initially you have 100% duration for the query, and after migrating to VictoriaLogs, you get 6% of out of the initial time. So you divide 100 by 6 or by 5 and get 20 times faster. So everything is great. I recommend you join VictoriaLogs and VictoriaMetrics community. We have Slack chat for VictoriaLogs and VictoriaMetrics. We have a special channel for VictoriaLogs in this Slack channel. We also have GitHub, obviously. All the source code is open source under Apache 2 license. And we are very glad to contribute. If you will decide to contribute to VictoriaLogs source code, or at least file some feature requests or bug reports, because it's very important for open source projects. We have Mastodon account. We have Reddit account and Telegram account and Twitter. So some useful links. The source code of VictoriaLogs is located on GitHub. VictoriaLogs also contains, I would say, better than average documentation for open source projects, because I'm very picky about the quality of documentation, because if you have no documentation, this means that users do not know how to use properly your software. That's why it's very important to have documentation, and this documentation should be high quality, easy to read and easy to understand by end users. And unfortunately, many open source projects do not pay much attention to documentation, but we pay. And you can follow me in GitHub, Twitter, and LinkedIn. I regularly publish some thoughts from my experience, from my life here. Okay, so we have 5 minutes. 5 minutes. Okay. Then let's return back to the questions, and I have a few surprise slides, which 10 minutes. Okay, which I added today an hour ago. I discovered a very interesting project in the internet, which is named Small Data Conference. Some people in San Francisco decided to organize a conference which is named Small Data Conference, contrary to a Big Data Conference. And the main point of this conference is that you can fit typical big data into a single computer on a single laptop. You don't need to run hundreds of nodes in a cluster mode for processing some big data. That's the main point of this conference, and I like this main point because it aligns well with what I achieve, what I try to promote here. That we, as you can see in this talk, you can store terabyte, literally not terabyte, but petabyte of logs on a single computer when you use a proper database. That's why it's very I want to propagate, to promote here. And I hope that this movement of small data will grow over time and will outshadow the movement of big data, which recommend you running hundreds of nodes, cluster of hundreds of nodes for handling some small amounts of data, terabytes of data. You can fit this terabytes of data or even petabytes of data on a single computer and get a faster performance of this and save a lot of costs. Oh, that's all. Oh, what happens? Oh, okay. That's all, and we can return to the questions if you have any. Yep.
So as I understand it, VictoriaLogs is a database, but does it ship with a way to view the logs, like a dashboard or a UI?
Yeah, it's okay. Let me repeat your question. Whether VictoriaLogs has some UI? Yeah, VictoriaLogs has built-in web UI. This web UI is mostly needed for logs investigation, quick logs investigation, and also VictoriaLogs provides a plugin for Grafana, which allows you building arbitrary dashboards in Grafana of data from VictoriaLogs.
Is it PromptQL or what kind of interface do you provide to Grafana?
The question was which query language is used by VictoriaLogs, is provided by VictoriaLogs for Grafana. The query language is unique. it's its own. It is named LogsQL. I designed this query language according to my understanding of what users need for typical investigation of logs, for typical analysis of logs. And this query language is very. I very like this query language. The end result, because it's very simple, it is concise, and it is very powerful. It allows you quickly filtering the needed logs and perform different transformations, data extractions during query time, and it allows performing you very big number of different statistics calculations. And you can calculate many different metrics, statistics in a single query, contrary to Loki, for example, because Loki allows calculating only a single metric per query.
Hey, I have Mike. So I have two questions, because I'm looking for specific features mostly. First of all, we need some kind of log immutability, so or non-malleable logs. So is there some way to like sign the log by some independent signature authorities? And then the second question, is it does this product allow like a multi-tenancy production?
The first question, the answer to the first question is VictoriaLogs doesn't provide any cryptographically secure signing of stored logs, but the good news is that VictoriaLogs doesn't allow you updating existing logs. So if you store logs into VictoriaLogs, you cannot modify them. You can only delete them, but the deletion operation isn't supported yet, but we are going to add it eventually. But the point is that you cannot modify stored logs. You can only delete in the future these logs, but this delete feature can be disabled. And the answer to the second question is yes, VictoriaLogs supports multi-tenancy out of the box, and it can handle literally tens of thousands of individual tenants without any issues contrary to Loki, because Loki can handle only, I would say, up to 100 different tenants because of architecture design. But VictoriaLogs can handle much more tenants.
Yes, your kind of like design space is a single machine with 64 terabytes of actual addressable storage. This a real story. I've done this in AWS. An EC2 instance can have 26 or 28 EBSs, 16 terabytes each. So on one machine, you can have about 450 terabytes of data. Would you run VictoriaMetrics on something like that, or you would horizontally scale at this point?
I would horizontally scale VictoriaLogs in this case. This example with 64 terabytes of storage is an extreme example, I would say, because when you store 64 terabytes of data, compressed data per node, this might make hard your operations, such as making backups or recovery for such big amounts of data. It will take literally hours for backups and recovering. And in this case, it is better to have some to find some balance between per node data, compressed data stored on the disk, and the number of nodes in cluster. And from my experience, 16 terabytes of data is much better than 64 terabytes of data per node. And this compressed data, if your logs are compressed at 50 times, for example, then you can cram 800 terabytes of data into 16 terabytes of data per node.
You mentioned that VictoriaLogs uses a Bloom filter for one of its optimization passes.
Yeah.
Is it possible to configure and tune this Bloom filter to match your needs better?
No, VictoriaLogs doesn't provide any configuration options for Bloom filters, and this is made deliberately. Bloom filters are enabled by default for all the stored log fields. And this decision is deliberate, as I said, because whenever we will provide this configuration option to users, this will increase chances that users will improperly configure it and get worse results than default results.
How does the roadmap look for VictoriaLogs or VictoriaMetrics in the future? Any new planned features or optimizations?
Yeah, we have a roadmap, and the main feature which we are going to implement in VictoriaLogs, main major feature, is ability to store historical logs to object storage. So it will transparently store historical logs to object storage and transparently query these logs.
A question on this. Will it be possible to store the logs completely in S3, so without local storage, or
probably
only local cache or something?
Yeah, probably. I have no good answer to this question currently. It depends on how this implementation for object storage will go. But initially, we plan to create this ability to automatically store historical logs to object storage. And after that, we will think about completely removing a local storage and storing all the ingested logs immediately to object storage. This case has some potential problems, I would say, with performance and latency for ingested logs, recently ingested logs, because object storage has 100 times bigger or even 1,000 times bigger latencies for disk operations, such as accessing these objects, and this might be not so good for performance, data ingestion performance. But I think that it can be resolved. Okay. So there are no any questions. Thank you for attending my call my talk, and try VictoriaLogs and provide feedback via GitHub or via other channels to us. I will be very happy to hear positive and even negative feedback, because negative feedback will allow improving VictoriaLogs.